Hi, I'm Chris. I'm Lila's father.
I'm Susan, Lila's mom.
I'm Chris, Lila's neighbor.
So my mom is going to be filming handheld. There you go. Alright. Hi, I'm Lila Munson, and today I'm going to tell you why the giant impact theory is the most credible theory to date on how we got our moon. Everyone's a little curious about the moon. You look up on a bright night or a clear day and you see it sitting up there. It doesn't really seem to do anything, but still, we wonder, where did it come from? Has it always been there? Did it break apart from the Earth, or did it fly by the Earth a little too close and get sucked into orbit? Well, not exactly. The scientific community agrees that the most widely accepted and least flawed theory on how we got our moon is the giant impact theory. It basically states that a small young planet, often called Theia, collided with the Earth and sprayed a massive amount of debris into orbit, and that accreted into our moon over time. I've always been a huge lover of the moon, so I've done tons of research, and I took 2 semesters of astronomy at PVCC. In order to determine how we got our moon, it's important to analyze the composition of our moon. William K. Hartman and Greg Harries from the Planetary Science Institute state that the Earth and the moon have almost identical oxygen isotope compositions, which is rare. Rocks and meteors from other parts of the solar system generally have different oxygen isotope compositions. Isotopic data is a way to determine both the composition and the age of an element. Researcher Alex Halliday states that isotopic data requires that the moon formed more than 30 million years after the start of the solar system, which means that the Earth was mostly fully formed by the time that the much younger Theia collided. The Earth and the moon have very similar compositions, but their densities differ. In the article Origin of the Moon, scientists Hartman and Harries state that the Earth has a mean density of about 5.5 grams per cubic centimeter, but the moon has a density of only 3.3 grams per cubic centimeter, which means that the moon is a little less dense than the Earth. Additionally, Canup's article, Lunar Forming Impacts, Processes and Alternatives, discusses how the Earth contains many more heavier elements, such as iron, than the moon, which accounts for the difference in density and the idea that the Earth was mostly fully formed upon the time of impact. Over time, the heavier elements, like iron, sink to the core of any planet. They're actually created in the cores of stars. Composition and density are important aspects of our moon, but it's also important to consider the orbit of our moon. The moon orbits on the same plane and in the same direction as the rest of the solar system. This is called the orbital plane. In the article, Lunar Forming Giant Impact Model Utilizing Modern Graphics, Island and colleagues discuss how, with the exception of Venus and Uranus, all of the planets in our solar system not only orbit in the same direction, but they spin on their axes in the same direction. Since the giant impact theory requires the moon to slowly form in orbit around the Earth, the moon would have settled into the same orbital plane as the rest of the solar system, as well as syncing up with the Earth's rotation, which gives us the light and the dark sides of the moon. It basically means that we only ever see one side of our moon. In conclusion, as Bennett and colleagues explain, the giant impact theory states that in the early life of our solar system, which was about 4.5 billion years ago, a young planet collided with the Earth. In Canup's article, Forming a Moon with Earth-like Composition via Giant Impact, he discusses how a bunch of debris from both planets spewed out into space around the Earth, creating a disk of debris that was from both planets. And this would settle into the natural orbit of Earth. This debris would accrete into our moon over time and would give us the strikingly similar composition that we observe and also the round shape of our moon. Since the Earth was already far enough into its development, the heavier elements like iron had sunk into the core, which created a less dense moon. Additionally, this theory accounts for the orbit of the moon. Due to the fact that the moon accreted over time from the disk of debris, the growing moon naturally set into the orbital plane and the Earth's rotation. So here I have a short clip of a computer simulated version of this theory. So as you can see, because Theia is much smaller and less dense, it pretty much just kind of explodes when it hits the Earth. But the outer layer of the Earth is what gets sprayed into orbit, while it leaves kind of the solid molten core behind, which, you can see how the debris kind of sprays out and then comes together into our little moon. Obviously it doesn't happen as fast as it happens in this video, but it's a really great visual to kind of show you why this theory makes so much sense. So just remember that the only reason that we have that pretty rock in the sky is because there was a giant impact that spewed a ton of debris into the orbit and allowed us to create, and allowed the moon to come together all on its own. Thank you.
Very good.